What if I told you there's a simple trick in Python that can make your code 10 times, 100 times, or even 1,000 times faster, maybe even more? And most people don't even know about it. So if you're writing slow loops or recalculating the same values over and over, you're probably wasting time. But there's a Python trick that fixes that instantly. I'm going to show you that right now. Jump into my editor and let's have a look at how we can do this. So let's say we have a function, and this function calculates the nth Fibonacci number. And that's a really common thing that you might encounter when learning coding. So let's make a basic recursive solution that calculates this. So for instance, I'm in the editor here, I'm in Visual Studio Code. I'm going to write this in Python. So let's say I have def for my function, pass in n, and what am I going to write? I'm going to say the following: if n is equal to 1, then return n. But obviously, for instances when that doesn't happen, we're going to be recursively solving this. So fib, I'm going to pass in n minus 1, and then I obviously need to plus that with fib for n minus 2. So that is a standard recursive solution for solving Fibonacci sequence. Now this works, but it is incredibly slow for large values. And why is that? It's because it can recalculate the same numbers over and over. And you've probably seen this before. You've probably heard people mention that it can be slow or really hungry. If you put in a massive number, watch your CPU grind to a halt. How can we fix this? The solution's really easy. Memoization. That's right, memoization. But instead of manually caching results, Python has a built-in feature for this. And it's just from the functools library. It's really simple. You've just got to add this one line to instantly speed things up. So rather than adding your own dictionary, we can use this built-in feature to immediately speed up this code. So what are we going to do? Okay, we'll need an import. Okay, so let's just carry on writing. So let's say from functools, I'm going to import LRU Cache. Okay, the cache is the key. We're going to be caching values. That's how it's going to make it so much faster. Now, what am I going to do? I'm going to use this in the following way. I'm going to use decorator LRU Cache, and I'm going to say max size is equal to none. And then I need to write myself a new function. So of course I could just copy this, copy it down here, but let's just call it something else. Let's call it cached fib, and of course change my references when I'm recursively solving here as well, cached fib and cached fib. Okay, now this will store previously computed values. So Python never recalculates the same result twice. And I'm going to create my own dictionary, I'm going to manage anything. I'm using the built-in feature that does it for me. It's amazing. Now, say you've done this, how can we prove that it's faster? I want to benchmark this and prove that it's much faster. So I'm going to use the timeit module to compare the normal versus cached Fibonacci functions. It's really simple. So what am I going to do? I'm going to import timeit, and I'm going to write some stuff out. I've got my function for non-cached and cached. Everything's great there. But we want to measure execution time. So I've written this out already, so I'm going to drop it right in here. So let's measure execution time for both the standard and the cached time. Great. So if you've not used timeit before, this may be a bit confusing to you, but it's fairly standard practice. And in fact, if you wanted to, I could create another video talking about timeit in another case. This is a great way to benchmark. I'm going to measure the actual computation time. Then we're going to compare the two, and I'm going to prove to you how much faster this method is. Okay, so how am I going to do that? I'm going to use some basic print statements with some f strings. Nothing particularly fancy, all very standard. So let's assume that the cache time is greater than 0, but if not, let's just add a little check, and let's say if it's greater than 0 to prevent any division by 0 errors, let's work out the speed up factor, which is how much faster it is to use the LRU cache than it is to not. So speed up factor is equal to normal time divided by cache time. Quite straightforward. Now what we want to do, we want to print some things out. So let's make some print statements. So I'm going to say the following. So I'm going to say without LRU cache, and let's say we've got normal time, and I'm going to format that with, there we go, 5, and we're going to say it is of course seconds. Okay, great. So that's without the LRU cache. So now let's have a look at with the LRU cache. It's another f string here. I'm going to say with LRU cache, and we're going to say cached time, of course. Again, we're going to format this, but we're going to go to more decimal points because it's potentially going to be much smaller. That's my expectation. Okay, and now let's print out the speed up. Okay, so we're expecting it to be a lot faster, but let's prove it. So we can say speed up, and we're going to say it's approximate, of course, and we're going to pass in the speed up factor. And we're going to do this to 2f. Okay, great. And we're going to say times faster. Okay, Everything looks good there. So this is if it's greater than 0 for the cache time, but we need to do something if it isn't. Okay, so let's do that now. So simply add our else clause. So let's print this as well. So we're going to get all of that, but we're going to say the following, rather than actually showing the two-digit factor because it is not greater than 0, it's essentially 0, which means it's too small to measure. So we're going to change this. So with LRU, we're just going to say too fast. 2G fast, too fast to measure. Great. Derp is going to be easily 1,000 times plus faster. Okay, great. That looks good to me. So all I need to do now is simply run this Python code, and we're going to output two, hopefully, very different time it values for the normal and the cached approach. So let's head on over to the terminal and let's run this. So here I am in the terminal. I'm simply going to run Python. I'm going to make this a bit bigger, in fact, to make it a bit easier to see what I'm doing. So Python caching, and let's see what we get. So look at that. Without the cache, 0.14245 seconds when we're using the Fibonacci with 30 for getting the sequence. With the cache, 0.000098660, and that is approximately 14,438 times faster. So I said maybe 10 times, maybe 100 times, maybe 1,000 times faster. This is 14,000 times faster by using caching. Now, of course, this is an illustrative example talking about a particular well-known function in Fibonacci. But the point is, by caching and using memoization, you can potentially extract huge gains in speeding up when doing this type of thing in your Python code. So there you go. The next time you have an expensive function with repeated calculations, just slap LRU cache on it and your code will run so much faster. And I think your CPU will thank you as well, which is never a bad thing. But hopefully, this is going to make your code so much more performant. You're going to look like a Python genius, the ultimate Pythonista, some might say. But I hope you found this helpful and you enjoyed this video. If you've got any questions, feel free to let me know in the comments and I'll do my best to answer them. But thanks for watching. Hope you like this. Feel free to like and subscribe and all that good stuff. And I can't wait to see you in the next video.